All right. Anybody have any homework questions or anything before I get going on this? All right, well, we're done talking about 1D particle kinematics, and now we're making a big jump to 2 dimensions, and the rest of the class is going to be in 2 dimensions. One thing that's sort of interesting is 1D and 2D are very different. You have to make some fundamental changes to things. We live in 3D, but actually in most cases going from 2 dimensions to 3 dimensions mathematically isn't very difficult. It doesn't really change much. So when you can deal with stuff in 2D, you can deal with most things in 3D. It's just a matter of one little extension you have to make. Okay. So now we're getting into 2-dimensional 2D kinematics of particles. And so again, let's just think about what all these things mean. So 2D now, it doesn't mean something moves along a line. It means something moves in a plane. So that's new. Up until now, things have been able to go one direction or the other. Now they have, at any instant, there's infinitely many directions they can move, but they do stay confined to a plane. And then kinematics and particles still mean the same thing they did before. You can think of kinematics as relationships between position, velocity, and acceleration. And a particle, remember, doesn't say anything about the object itself. It's just how you're treating it mathematically. And it says that the object, you treat the object like it exists at a single point. It exists as a point located at the object's center of mass. So basically the middle of the object. You can't talk about an object's orientation when you're talking about particles. That's important. You can't differentiate different spots in the object mathematically, and you can't say now it's facing north, now it's facing west, that kind of thing. There's no such thing as orientation of a particle. Okay, so there are a few things I want you to remember about what we did in 1 dimension. In 1D, position, velocity, and acceleration had magnitudes and directions. Mathematically, we could represent the direction with a positive or a negative sign. So we could represent the directions with a plus or minus sign. But you could also just as easily, I mean, it's not as useful mathematically, but just as easily, you could represent the direction by just drawing an arrow in the direction of the thing. So notice, keep in mind that we could have also represented the directions with an arrow. So you could also represent 1D directions with arrows. So let me show you sort of what I'm talking about. So if you had an object that's so let's say that this is our positive direction and this is our negative direction. And let's say that this object at the instant that we're talking about has a velocity of negative 30 meters per second and is slowing down. Okay, well, what do we know about the object? Okay, so this is the object. The velocity is negative 30. So that means the velocity you could think of as an arrow. You know, the direction of the velocity is an arrow going in the negative direction. And if it's slowing down, velocity and acceleration have opposite directions. So that means the acceleration is this way. Okay? So in order to do math, we use the signs, the plus minus signs, but you could just as easily draw those arrows on your picture to show the direction. That's going to be like an important thing to keep in mind as we go into 2 dimensions. Well, the reason that we could use the plus minus signs as directions mathematically is because, so the reason that in 1D you can represent direction with a plus or a minus is that at any instant, there's only 2 directions you can go, and there's 2 signs, so it matches up, you know? So at any instant, there are only 2 directions. So you call one of them positive and one of them negative, and it works out fine. But that's not going to work anymore in 2D. Because, you know, if this is the location of the object, it can move this way or this way or this way, infinitely many directions, you know? So there's infinitely many directions and only 2 signs. So we're going to need a new way to mathematically deal with directions in 2D. You know, we're going to need a new mathematical approach to directions for 2-dimensional motion. Anybody have any questions about what I'm talking about so far? So why we're making this, why we're going to have sort of this fundamental new way of approaching 2-dimensional stuff. So this new mathematical approach that we're going to use for 2 dimensions is called vectors. And so before I get into two-dimensional kinematics, we're going to pretty much spend all of today just talking about what we need to know about vectors. Okay? Vectors are like numbers. They're mathematical objects. And we're going to use these vectors to do calculations in 2 dimensions. And one thing about vectors, position, velocity, and acceleration now are all going to be vectors. And when a variable is a vector, we denote it with an arrow over the top. So that's how you know that this variable doesn't hold a value like -5 or 7 or something. It holds one of these vectors in it. And so we're going to denote the position vector like this, velocity vector like this, and acceleration vector like this. Okay. Time still is going to be the same as it was. That doesn't change in 2 dimensions. It still just goes forward like a stopwatch. So time is still the same as it was before. And it just represents what the stopwatch says. So think of a vector as an arrow. And it has only 2 properties. The first is a magnitude. And this is represented by the length of the arrow. And the second one, obviously, I've been talking about how this is a new way to represent directions. So the other property of a vector is a direction. Okay, so these are all vectors. You know, there's a vector with a small magnitude that's pointing to the lower left. It's in the direction to the lower left. This one has a larger magnitude. It's in the direction to the upper left. And when I talk about these things, the part that doesn't have an arrow, you know, that doesn't have the point on it, is going to be called the tail. And the part that does have the point on it is going to be called the head. And so, like the position vector, velocity vector, these things, you could always represent them as arrows that show the direction it's moving, and that has the arrow's length is the magnitude. So let's think back to 1 dimension, you know. We could have done the same thing in 1 dimension. This thing has a velocity of -30. Well, we drew an arrow in the direction. All we'd have to do is, you know, choose that 1 millimeter is equal to 1 meter per second, say, you know, and then just make it 30 millimeters long, pointing in the negative direction. Okay, and this one, oh, that was the velocity. I didn't tell you what the magnitude of acceleration is, but again, the length, you could just represent how big that acceleration is, and we have it pointing in the correct direction. Okay. But how you use those for math isn't that clear. To do math with vectors, we're always going to break vectors down into what's called their components. So we'll express them as components. Okay, so here's what components mean. If this is the vector, okay, you can break that up into a vector that's parallel to the x-axis and a vector that's parallel to the y-axis. So notice that to get to the tip of this vector, you'd go this far along the positive x-axis. And then from there, you'd go this far along the positive y-axis. And you're at the tip. Okay? This is called the x component. And this is called the y component. And as far as coming up with the components of these vectors, this is the most important thing to remember about vectors. So the most important fact about vector components. That is, if you put the tail of the vector at the origin of the coordinate system, at 0, 0 of the coordinate system, CS's coordinate system, the components of the vector are just the coordinates of the head of the vector. The components of the vector are the coordinates of the vector's head. So what that means is if you can find the coordinates of a point, you can find the components of a vector, okay? If you can find the coordinates of a point, you can calculate the components of a vector. So, you know, just to get an illustration of this in your notes, if your vector is like this, and this is the x-axis, and this is the y-axis. And let's say this is 1, 2, 3, 4, and 1, 2, 3. Okay, so -1, -2, -3, -4. This is +1, +2, +3. Then the coordinates of the head are -4, +3. And that means that the components of this vector so the x component of the vector is -4, and the y component of the vector is +3. Okay, there's a few ways to write components of vectors. Not everybody does it the same way. They all mean the same thing, though. So there are multiple ways to write the components. One way is -4 times I with this little hat. If you write a number times this I with the hat, that means that the number is the x component. And then plus 3 times j with a little hat. So that's a way that a lot of people write vectors. Okay? We're going to use this notation. We're going to use the notation -4 and then 3 under it in square brackets. Okay? So it's a lot like just writing the coordinates, but it's square brackets instead of curved brackets, and the numbers are on top of each other. But the top one is always x, and the bottom one is always y. So this is the notation that I'm going to use. But if you ever see someone write this with an I and a J, try to remember that that means the same thing, you know? There's nothing different about that. It's just a different way of writing your answers. One thing that is helpful about remembering, what I said is the most important fact about these components. If you remember this relationship between coordinates and vector components, coordinates of the head of the vector and vector components, you can always figure out what the signs of the components should be, okay, just by eyeballing the direction. So one thing I want you to notice is from the relationship between coordinates and components, you can always see immediately what the signs of the components should be, or what they are, I guess. Okay, so let me do an example showing what I'm talking about. What are the signs of the components for each vector below? So the first one is this way. The second one is this way. The third one is this way. And the fourth one, what am I still missing? This way. Yep. Scroll up, yeah. Okay, so let's think through what the signs are of these components. So for part A, each time, I mean, it won't take very long before you don't have to draw this coordinate system at all, but I'm going to start by drawing the coordinate system. And I'm going to take that vector and just move it so that the tail is at the origin. And now just think about what the signs are of the coordinates. What's the x component of this point? Sign, positive or negative? Negative, yep. So the x component is negative. What about the y component? Positive, yep. So we know from this that the x component is negative and the y component is positive. So for the second one, the vector is like that. Is the x component of this vector positive or negative? Negative. And is the y component positive or negative? Negative, yep. Anybody have any questions you want me to answer to help clarify this, or is everyone sort of understanding what I'm doing here? C, well, maybe this time I won't even put it on the coordinate system. You can see that that's in that first quadrant. So what's the x component going to be, positive or negative? Positive. And the y component? Right. Any questions about that one? And then the last one, what's the x component? Positive. And the y component? Negative, right? Now, what about vectors that are parallel to coordinate axes? You know, what about vectors that are directly along a coordinate axis? Then it's going to be So I guess let me do this with an example. So let's say that we have a vector that is straight down, and we know that the magnitude of it is 5. Okay. Then here's the coordinate system. Put the tail at the origin. And so do we know what the coordinates would be of that point that's 5 along that black arrow? It's very close, but it's instead it's 0 along the x, which we always just list first, and then -5 along the y. Okay, so this is just going to be 0, -5. So it's especially easy to come up with the components if you're along the positive x or negative x, or positive y or negative y. Okay. Yep.
When you do the bracket thing, you did the one bracket earlier, we're supposed to do 2 or 1. Like in the x-axis, you can first example thing going to one bracket, up. Oh, I did put 2 there. Never mind.
Oh, okay. Yeah, should be 2. Yep. Okay. So what if you're given? So if you're given a magnitude and the vector lies directly along one of the coordinate axes, coming up with the components is easy. That's just like this. Okay. You know, I guess let me do one more. So if it's this way, let's say this has a magnitude of 3. You can see that that arrow's in the positive x direction, and so that vector is just going to be 3, 0. If instead of this, you're given a vector as a length L, and an angle with respect to some reference line, so for example, let's say that we're given a vector like this that we say has a magnitude of 10, and it's 20 degrees from the vertical. Okay, how are we going to come up with the components for that? Well, the first step is find the counterclockwise angle theta. From the positive x-axis to the vector. And then second, the components of the vector are just going to be L times the cosine of that angle theta, that's the x component, and L times the sine of that angle theta is the y component. Okay, so let's do a couple examples of this. Well, let's start with the example I gave here. Find the components of the vector with a magnitude of 10, and it makes an angle of 20 degrees from the vertical. Well, start with the coordinate system. And put the tail of the vector at the origin. We're given that this angle is 20 degrees. But that's not the theta we want. The theta we want is from the positive x-axis counterclockwise to this vector. Okay, so this angle here is the one we want. So what would that angle be?
70.
Yeah, so this is 70 degrees. And so the components are 10 times the cosine of 70, 10 times the sine of 70. And that comes out to be 3.42 for x and 9.40 for y. So in a coordinate system, we're going to, for these, just keep using a coordinate system oriented this way like we're used to. We want to find the components of these vectors. So for part A, let's say it has a magnitude of 5, and it makes an angle of 30 degrees with the horizontal. And for B, it has a magnitude of 10 and makes an angle of 20 degrees with that vertical. Well, take a couple minutes and see if you can go through these, follow the steps of calculating the components of those vectors. Feel free to talk to each other or ask me questions, and then I'll go through it just to make sure. Okay, so for the first one, so I'm going to start by drawing the coordinate system. And I'm going to draw the vector. It has a magnitude of 5. And this angle is 30 degrees. So what's the counterclockwise angle from the positive x-axis to the vector? In this case, since all we want is just think of starting at the x-axis how far do you have to rotate counterclockwise until you're lined up with the vector? And so it's just 30 in this case, just positive 30. Okay. And so the components of this vector are 5 times the cosine of 30, 5 times the sine of 30. And if you plug that into your calculator, you get 4.33 for the x component and 2.5 for the y component. And if you plug it into your calculator and don't get that, it means your calculator is probably in radians. So if you can't figure out how to switch back and forth between degrees and radians, just come talk to me. It's just a mode button somewhere. But in this class, when you use sine and cosine, you're just always going to be in degrees. So for this class, you never have to be in radians. I don't know, if you're taking math also, you might have to switch sometimes. Okay, part B. So again, I'm going to start with the coordinate system. And the vector has a magnitude of 10. And this angle is 20 degrees. So what's the counterclockwise angle? If you start at the positive x and go counterclockwise, my pen. So start at x, go counterclockwise until you're lined up with the vector. What is that angle? It's going to be 90, 180. You can think of it as 270, but we didn't quite get there, so you have to backtrack 20. So it's going to be 250 degrees. So this is going to be 10 times the cosine of 250, 10 times the sine of 250, and so that is going to be negative 3.42, negative 9.40. Yep.
We have 250 part.
So there's kind of two ways you can think about it. One is that this angle is 70. You see that? So you can, every time you go from one axis to the next one, it's 90 degrees. So if you start at x, it's 90 to get here, 180 to get here, plus another 70. So 180 plus 70 is 250.
And then you always start at the same spot, then you go counterclockwise again?
Yeah, you always start lined up with the positive x-axis.
Okay.
Yep. You also can go clockwise if you call that angle negative, and sine and cosine will still give you the same thing. So if you start here, you could go negative 90 minus another 20, so negative 110. No, yeah, 110. And so then it would be 10 times cosine and sine of negative 110, and that would give you the same numerical answers. Okay. Okay, how about one that's going straight up like this and has a magnitude of 3? What would be the components of that one? That's right. So this would be, so there's two ways you could do this. 3 cosine of 90, 3 sine of 90. Cosine of 90 is 0. Sine of 90 is 1. So you get 0, 3. But remember that you also, since this just lines up with the positive y-axis, you can just see right away that this is going to be positive 3 in the y direction. Okay? But those two ways of doing it agree. They have to agree, so. Okay, so now I'm going to do something that I don't think they do really in math classes very much, because this isn't, like, to someone in math, this isn't really relevant to anything. But there'll be times when, for us, we're going to want to use rotations of the coordinate system other than just this standard orientation. Okay, so let's say that we have this vector. Let's say it has a magnitude of 10 and makes an angle of 40 degrees there. Okay. And we want to know, what are the components of this vector? And we're going to do it in different coordinate systems. So first we're going to choose just the coordinate system we're used to seeing. Second, we're going to do a coordinate system let's do the x-axis this way, the positive x-axis that way, and the positive y-axis this way. And then third, we'll have it rotated where this is x, this is y, and the x-axis is 40 degrees from the horizontal. So those are the three coordinate systems that we're going to use to calculate the components of this vector. We'll just do them one by one. Okay, so the first one, this is the one we're the most used to. Put the tail of the vector at the origin. We know that this angle is 40 degrees. So what's the counterclockwise angle from the x-axis to that vector? Yeah, it would be 90, 180, plus 40, so 220. So the vector components would be 10 times the cosine of 220 degrees, 10 times the sine of 220 degrees, and that would give you negative 7.66 and negative 6.43. Any questions about that one? Okay, so now same vector, but a different coordinate system. So this time our x-axis is pointing down. and our y-axis is pointing that way. And without doing anything to the vector, I'm still just going to take the same vector and put its tail at the origin. So this angle now is 40 degrees. Okay, so the vector is the same, but the components are going to be different because we have to start our angle at the positive x-axis. Okay, so we have to start here now, not here like in this one, and go around counterclockwise until we hit this. So what's that going to be? 90, 180, 270, plus 40 is 310. Or you could also just, if you recognize that this angle is 60 degrees, you could just call it negative 60. You'd get the same thing. Okay, but I'll call it 310. And so you get 10 times the cosine of 310, 10 times the sine of 310, and you get positive 6.43, negative 7.66. Now, a lot of this, I'm just kind of asking you to just sort of trust what your calculator gives you. You know, you come up with those angles, you plug it in, it tells you something, and you just have to trust it. But remember that you can always check to make sure that the signs are right based on what you know about the coordinates of the head. Okay, so let's think about this one in part A. The head is in the third quadrant. So you would expect the coordinates to be negative and negative for both of them. And so if you got that for your answer, it gives you confidence that nothing went wrong in your calculation. Okay. What about this one now? Well, this is what you're not that used to, but the first quadrant is the one between the positive x and positive y. So it's going to go first quadrant, second, third, fourth. Okay. This vector is in the fourth quadrant. So you would expect it to have a positive x component and a negative y component. And that's what we got. So I would recommend getting in the habit, at least for the first couple weeks that you're dealing with vectors, just make sure you always look at your answer and make sense out of the signs. Is that what I expected to get for the signs? Okay. Oh, and then the last one. So for this one, the coordinate system is crooked. And this angle is 40 degrees. That means that when you draw your vector with its tail at the origin, the vector just looks like this. With a magnitude of 10. Because you never rotate the vector, you just take the vector as it is and put it on the coordinate system. And that's how it would line up. And so you can just eyeball this and say, okay, it's on the negative x axis. So it's going to be, the x component is going to be negative 10. The y component is going to be 0. You also could say, okay, that's an angle of 180 degrees, and sine and cosine would give you that same thing. Well, there's a reason that we express vectors in component form like this. It's just that it makes the math a lot easier. So now I want to talk about how to do math with vectors once you have them expressed as components. So this is vector math using components. The first thing we're going to do is add two vectors. So if you have these two vectors, the first one has components A, B, and the second one has components C, D. Adding these two vectors gives you an x component that you get from just adding the two x components, and a y component that you get from just adding those two. So for example, if you're adding the vector 5, -5, and the vector 1, 6, add the two x components, you get 6. Add the two y components, you get +1. In our lab this week, we're going to spend a bit of time talking about intuitively what it means to add vectors and to do some of these other calculations. And there is like sort of a physical, intuitive meaning to this stuff that we'll talk about, but this is the easy way to do the math. Come up with the components and then just follow these steps. Okay, besides adding two vectors, something we're going to do a lot. So the second thing we're going to do is multiply a vector by a number. Okay, so if you have a number C that you're multiplying to a vector with components A, B, the way you do that math is multiply C times the x component, so CA is the x component, and then multiply it by the y component to get the new y component. So for example, if you multiply the number -6 to the vector components -3, 4, -6 times -3 is +18. -6 times 4 is -24. And then the third thing that we won't do too often, but sometimes you'll be given components of a vector and you'll want to figure out the magnitude. It's more common that we'll be given an angle and the magnitude, and then we want to come up with components. But sometimes you might want to go the other direction. So this is if you want to calculate the magnitude of a vector. So if you have a vector u that has components a, b, then the magnitude of that vector, the notation for that is like the absolute value of a vector. And you do that as the x component squared plus the y component squared, all square root. Okay, so let's, for an example, let's use some vector components that we have had. So okay, in this example, we start with a vector, we're given the angle, and we're given a magnitude of 10. Okay, and then we figured out the components. Well, let's just take the first set of components we got. If we calculate the magnitude of this vector, what do you expect we would get? It came from using the fact that the magnitude was 10. So if we take these components and calculate the magnitude, we should get 10 back. Okay? And so let's say we want to calculate, so let's say we have this vector, what was it? Negative 7.66, negative 6.43. So negative 7.66, negative 6.43. Then the magnitude of that vector is the square of negative 7.66 plus the square of negative 6.43, all square root. And if you plug that into your calculator, you get 10. Any questions about that one? Why does that work? It's the Pythagorean theorem. Remember, if you have a right triangle, what it says is if this is A and this is B, then this one is A squared plus B squared square root. Well, A is the x component, B is the y component, and so that's what you get. And this hypotenuse is like the, that's the vector itself. So the length of that hypotenuse is the magnitude of the vector. Anybody have any questions about that? Okay, well, that's a good place to stop, I think. So I'll give you some vector problems to work on. And then on Wednesday, we'll start talking about what a position vector and a velocity vector and acceleration vector mean and how to connect those to this math.